So today we will do gauge pressure or gauge pressure. What is gauge pressure and absolute pressure? Gauge pressure and absolute pressure. Let's see what are they. See, as the name suggests, if you have any particular pressure instrument to check, it is this, what is it going to measure it? So it is defined as the excess pressure above the atmospheric pressure is called gauge pressure or gauge pressure. So what does this mean? We know absolute pressure at any point is given as P is equal to P atmospheric plus H rho G. So if you subtract this, P minus PA equals to H rho G is called the gauge pressure. This is called the gauge pressure or gauge pressure. Let us see an example to understand this. If I give you an example, let's say I take one vessel, one bottle. We will do one more numerical on this kind, but let's say I take this one. It is carrying water. Its height is, let's say, 50 centimeter. So what is the absolute pressure? What is the absolute pressure? Absolute pressure and gauge pressure acting at the bottom. So how will you find bottom of the container? So it's simple. What do you have to do? So this is rho equal to, as we know, density of water is 10 to the power 3 kg per meter cube, and the bottom is, to find this one, what are we going to do? P equal to PA plus H rho G. The pressure at the bottom would be 101,300 plus H rho G, 50 centimeter. That means 0.5 into 1000 into, I am taking this as 10, you can take this as 9.8. So if we solve this, one, I get here 101,300 plus, that gives me 0.5 into 1000 into 10, that gives me 5000. So 10600 Pascal. So this is the absolute pressure that is acting at the bottom of the vessel. So this is the absolute pressure. Now what is the gauge pressure? To find the gauge pressure, what do you do? Subtract this. So if you look at this expression, P bottom minus PA atmosphere will give me 0.5 into 1000 into 10 Pascal. That gives me 5000 Pascal. So this is gauge pressure. This is called the gauge pressure. So that's the difference between gauge pressure and the absolute pressure at any point. So let us take the swimming base problem once again. A person is swimming in sea water. At a depth of 9 meters below the sea level. This is, you can try it, homework. Find the absolute pressure and gauge pressure. Acting over the person. Okay, so this is how we can find out. Let us see this in another example. So this one you can do it at your homework. Another question I can give you. Okay, let's do this question. Okay, let's go to the next page. Let's say this is any bottle. This is the base of the bottle. The bottle has a cap. The bottle is fitted with a cap. Now, the height of this bottle is 20 centimeter. The mass of this bottle cap, this is the cap, the mass of this cap is 15 gram. Let's say this is 15 gram. The base radius is, the radius of this base, if I take a center from here, the base radius is 12 centimeters and the top radius is 4 centimeters. This is 4 cm, 4 centimeter. It carries water. We are interested to find how much force should be applied should be applied to the top of the cap to break the bottom, to break the bottom surface. Okay, so take, it is known the bottom surface breaks at F equal to 1000 Newton. So if our total force acting on the bottom one is greater than 1000 Newton, we know the below the bottom surface is going to break and the water will fall. So how do we do this? So we'll be using the Pascal's principle. Using Pascal's principle, we know pressure at the bottom would be pressure at the top, that is atmospheric pressure, plus H rho g, plus, you see the cap is tightened, the cap is fixed. So you when you are fixing it, when you are tightening the cap, it is also putting some pressure on the water. So that means there is a pressure of the cap. Therefore we can write pressure at the bottom will be 101,300 plus H is 20 centimeter. So 20 into 0.2 actually, sorry, 0.2 into 10 into 1000 plus pressure of the cap. So cap will be, what we can write, mg. So mass is 15 gram. So 0.15 into 10 divided by base area. So it's force by area. We are using the concept here, force, pressure is force by area. So here pressure is 4. So force is, area would be pi r square. So 4 centimeter. So we can write this as pi into 4 0.04 whole square. So this is how we can solve this. So if I solve this one, what will we get? If I solve this, so first of all let us solve this one. 0.15 into 10, that gives me 1.5 divided by pi into 0.04 into 0.04. Okay, so we get this 298. So 101,300 plus 0.2 into 1 into 1000 plus I get here 298.42. So if I solve this further, 0.2 into 10 into 1000, I get here 2000. So 101,300 plus 2000 plus 298.42. So if I add them, I get here plus 101,300 plus 298.42. It gives me, the value comes out to be 103,598.42 Pascal. This is the pressure acting at the bottom. Acting at the bottom. So pressure at the bottom, total will be what? What force you need to apply? So with this force you need to apply an extra force which will break it. You need to apply an extra pressure to break it. So it should be pressure at the bottom plus that pressure extra which you need to apply. So pressure extra will be nothing but force per unit area, that is pi into 0.04 whole square. So therefore we can write this value we have got. So this value, so this is what we need to get. But wait a minute, this is the absolute pressure. We are only dealing with only this much. Why do I need to take it from the top of the atmosphere? So I can easily remove the atmosphere here and I just only need the gauge pressure here. How much is the pressure only in this region? In this removing the atmosphere, what is the pressure needed? That is only we need. So what are you going to do? We're going to find the gauge pressure. So pressure gauge will be, so pressure bottom I am writing once again, will be this value 103598.42 minus 101300. So this becomes my bottom gauge pressure. So if I subtract this, I get here minus 101300. I get here 2000. So this is the gauge pressure, 2298.42 Pascal. So this is the gauge pressure of the bottom. Let us use it now. So what will be the total? So pressure bottom total will be equal to this value 2298.42 plus pressure extra. It is this extra force that I need to find. So what I'm going to write now, force at the bottom total. Okay, so bottom total we know it can handle at the most 1000. So pressure bottom total divided by pi. How much was the base? I made it 12 centimeter, right? Okay, pi 0.12 whole square equal to 2298.42 plus here force by, we are hitting at the cap. We are hitting at the cap. So pi 0.04 whole square. So I need to find this force. This is already given 1000 Newton. So I'll put here 1000 divided by pi 0.12 whole square is equal to 2298.42 plus F by pi 0.04 whole square. So we will solve this one now. So if I solve this, let's see how much I get. I'm using calculator. Please don't use a calculator in your exam. This is not allowed in Central Board of Secondary Education. So 1000 divided by pi into 0.12 into 0.12, I get here 22104.85 equal to 2298.42 minus F by pi 0.04 whole square. Let us subtract
plus.
plus. So let us subtract this now. So if I subtract this, so 2 minus 2298.42 gives me 19806. So I'm going to get here 19806.44. I'm incrementing by 144 equal to f by pi 0.04 whole square. So if I multiply this, f will give me into pi into 0.04 into 0.04, that gives me 99.55 99.558 Newton. So if you apply with this force at the top, so if this is our container, maybe mathematical error, you have to go through it once. If I have done correctly, you redo this with all your own data. So if you apply this one with this force 99, let's say with 100 Newton only, I'm saying approximately, if you apply this with 100 Newton with a base radius of being 12 centimeter, so the base of the bottle won't be able to withstand the pressure and it will break, and it is going to break. This is a common situation in the kitchen. You will find there are many pots, many containers where you keep if you keep objects, you just cannot keep everything in every container. For example, you cannot keep honey which is very thick on a very thin container. For honey, it has to come in a very well built and well mechanical property of solids, I mean good elastic property or strong properties, the material which is holding these strong properties. Only on those kind of jar you can keep the honey, because if you give someone gives a force from any side, so this is what is going to happen, and it is going to break. The container is going to break. So this is the point to be noted in this case. Okay, now let us come to, so you can try this homework. I'm giving you one more.
Sir.
You can try it. I'm giving you a similar problem I'm giving you, but I'm changing the values. You can try it. Go through this. Let us say this is some kind of pot. I'm making it a little bit difficult now, but the process is same only. Let's say this is 15 centimeter and this is 5 centimeter. Okay, it carries an oil. Let's say it is holding an oil. Some kind of oil is present here, whose density rho is 800 kg per meter cube. The base can withstand at the most, okay, by the way, this is 20 gram and its radius is, I've already given it to you, 5 centimeter. This is 15 centimeter and height 30 centimeter. So if the braking force is, why don't I give you the braking stress? Okay, let us give you the braking force only, no problem. Braking force of the bottom, let us keep it to simple 1000 Newton only. 1000 Newton. Then find the force with which when the cap is being hit will break the vessel bottom. So do this as a homework. So let us do one more topic, that is called Torricelli's barometer. Torricelli's barometer. Please check the spelling. I am little doubtful about the spelling. He is an Italian scientist, Torricelli. Torricelli's barometer. So what is it? He wanted to find the atmospheric pressure, or he calculated the atmospheric pressure, and he did it. His apparatus included. What did he do? Torricelli, the Italian physicist, he took a vessel. Filled it with a mercury, and then he took a test tube, and the test tube, he first make the test tube stay in vacuum, that the inside the test tube there is a complete vacuum, no air substance is present there. And then what did he do? He dipped the test tube like this. And when he dipped it, then what happened is that in the glass you will see mercury is going to make a convex meniscus like this. Similarly here also, what he observed, that the mercury gradually rise inside the test tube, and is reached to a certain height h. He found out this height to be 0.76 meter. This height he found 0.76 meter or 76 centimeter or 760 millimeter. This is 8G. So what did he do? A test tube, an evacuated test tube. When dipped inverted, in a trough carrying mercury, it is observed mercury in the tube rises in the mercury in the vessel, not tube, mercury in the vessel rises in the tube up to certain height h. The recorded h at sea level is found to be 0.76 meter, okay, or 760 millimeter. Mercury is chosen in this barometer. Mercury is used in this glass barometer because mercury do not stick to the walls of the glass vessel and the tube. So no loss in the volume of Hg. Now you can consider 3 points here: A, B and C. This is point C. At this point we have the P atmospheric pressure, P atm. So what are you going to do? The point A and B are at equal atmospheric pressure. That is, PA is equal to PB, and pressure above the mercury column in the tube this PC equals to 0, since PC is vacuum. PC is at, since C is at vacuum, since C is at vacuum. Therefore, what can we write? Pressure at the bottom, that is pressure at the B, is equal to pressure at the top, which is C, plus H rho G. But PV is equal to PC, as we have seen here. Therefore, we can write PA is equal to PC plus H rho G. But PC is 0. PC equal to 0. Therefore, PA is equal to H rho G. So H is, as you have seen, the observed value is 0.76 into density of mercury is 13.6 into 10 to the power 3 into 9.8. So if we do this, we're going to get the value to be so if we do this one, you see 0.76 into 13.6 into 1000 into 9.8. We get this as PA is approximately 101,292.8, which we write this as 101300 Pascal or atm, 1 atmospheric pressure. Okay, this is 1 atm. So 1 atm is also, another unit of 1 atm would be 760 millimeter of mercury or 76 centimeter of mercury or 0.76 meter of mercury. So this is the another unit. When you go for blood pressure monitor, when you use any blood pressure BP monitor to check your blood pressure, actually this is the scale what we use it. So you see, in this chapter it is very important that you stay familiar with different units of pressure, because pressure has been used in has multiple applications, and in different applications it has been used in different units. For example, when you are going to inflate your car tire, you will be using the unit as PSI. When you are going for some other pressure, you are putting force per unit area, then it is better to go for Pascal. Now in case of blood pressure meter, liquid flow, 76 millimeter of mercury is another unit of pressure which is used. So what you can do, you can try this question as a homework, is that in Torricelli's barometer, if instead of mercury a fluid, a liquid of density 1000 kg per meter cube is used, then how high will the liquid column rise in the tube for 1 atm. 1 atm. So now if we will calculate the height of atmosphere, how high is our atmosphere? So as we know that if this is any air column of height h, this is any air column of height h, it will exert an air column of height h will exert a pressure of 1 atm or 101300 Pascal or 76 millimeter of mercury. That is, we can write H rho g is equal to 101300 Pascal. Therefore, H would be 101300 divided by rho g. So 101300, density of air is 1.27. So 1.27 into 9.8, taking density of air to be uniform, density of air to be constant, which is actually not. So we can find, if I do this, I will get here 101,300 divided by 1.27 into 9.8. That gives me 8139. 8139, approximately 8 kilometers. Approximately 8 kilometers. The height of our atmosphere is approximately 8 kilometers. Okay. So this is how you can find out the height of the atmosphere. Now, one more question. What you can do, take one question as homework. A column of water column of water column of water 40 centimeter high supports a 30 centimeter column of an unknown liquid. What is the density of the liquid? Find this. What formulas to use, you please find. Density of blood, I forgot to give you this earlier, is raw blood is 1.04 gram per centimeter cube. Gram per centimeter cube. Let me write it in the beginning. Somewhere I given you the density chart here. I'll include it here as well. So density of blood is 1.04 gram per centimeter cube, which will give you 1.04 into 10 to the power 3 kg per meter cube. Then what is the minimum? Then what is the minimum pressure required? Minimum pressure required to force blood from blood from foot of the person, from the foot of the person to the head, the foot of the person to the head, height of the person is 6 feet. Neglect friction. So 6 feet. I must give you one scale here. 1 feet is equal to 30 centimeter or 0.3 meter. So calculate here. 1 meter would be equal to then how much feet? So 1 meter would be equals to 1 by 0.3. That gives me little bit more, so something 3 point something. So 1 divided by 0.3 gives me around 3.33 feet. So 1 meter is actually, use this, 3.33 feet. Use this to solve it. Okay.